tonight we have, unfortunately, last public lecture at this by our distinguished speaker, Professor from MIT, Nergis Mavalvala. Professor Mavalvala has worked on the development on exotic quantum states of light, and in particular, the generation of light in squeezed coherent states. By injecting such states into the kilometer-sized Michelson interferometer of the light detector, the group greatly improved the sensitivity of the detector by reducing quantum noise, thereby making a great contribution into the detection of gravitational waves and opening a new window in the universe. It is our pleasure and honor that tonight, she will give a public lecture titled Opening a New Window into the Universe, the 100-year quest for Einstein's gravitational waves. Please join me to welcome very warmly.
Thank you, Alikram. Thank you. So hi again, everybody, and hi also to the new people who've come into the room. So for those of you who've already heard me talking to you for several hours already, my apologies, but here I am again. I'm going to tell you about things that you already know, which was not true this afternoon, right? Okay, good. All right, so look, the title of my talk is Opening a New Window into the Universe. Now, obviously, if I'm going to tell you about the new window into the universe, the first thing I must tell you is what was the old window into the universe. The old window into the universe was light. As we all know, for millennia, humans have looked out into the sky and we've pondered what's out there, and that information has come to us through light, which for most of our history we looked at through our own eyes. That changed in the last few hundred years, and I'll say a little bit more about that later. So my story on this new window starts with the 2017 Nobel Prize in Physics, which was given to Ray Weiss, Kip Thorne, and Barry Barish for decisive contributions to the LIGO detector and the observation of gravitational waves. And the announcement for the Nobel Prize began with, "This year's Nobel Prize goes for a discovery that shook the world." So that was their quote, and I really liked it because what I hadn't anticipated in the 25 years that I was working on this problem of detecting gravitational waves, I hadn't really appreciated that it would literally shake the world in terms of the impact that it had in society. And I'll talk a little bit about that. So, of course, we shake all the time because gravitational waves are going through us, but those were special because we could actually measure them, and they also made a bit of an impact outside. So our first messenger that has withstood the tests of time is light. This used to, by the way, be my favorite image in astronomy. This is Cassiopeia A. It is actually a supernova remnant. So what it is it's a composite picture that's made using NASA's 3 great space observatories. So the red and orange parts of the image are actually infrared light that are made using taken with the Spitzer infrared space telescope. The yellow and green parts are the Hubble Space Telescope, which is visible light, and then finally the purple and blue parts of the image are taken using the Chandra X-ray Observatory. Now, part of the reason I like this particular image is, of course, that the technology that goes into making it is spectacular. It is itself spectacular, and it reminds us of something very important, and that is that if you only look with one color of light, you can miss important things. So if you look in the very center of this image is a small dot that emits only in the X-ray. and that is the neutron star that was the remnant of this supernova explosion, and it only emits in the X-rays in this image. So what happened to this particular object was that about 340 years ago, it was a star. It was an ordinary star that had run out of nuclear fuel, and because of that, it could no longer hold itself up against its own gravity, and it went supernova. So this is a supernova remnant, and it actually has at the center this little neutron star. Now, if this parent star had been heavier than about maybe 3 solar masses, instead of collapsing down to a neutron star, this object would have collapsed down to a black hole. Okay, and so that's sort of the dividing line, 2 to 3 solar masses. So that was how we were studying the universe. Now imagine that this object had been a black hole. How might we then observe it? Well, it turns out that we would be hard-pressed to try to observe a black hole, especially a black hole not surrounded by gas and dust and matter with light, because it would not emit any. And so we would like to use a messenger that brings information about black holes, and that would be gravity. So what do we know about gravity? Well, in the 17th century, we had Isaac Newton, and he had a very successful theory of gravity. Actually, it was a theory that was also seen to be one of the first quantitative pieces of science, where he said, well, if you have 2 masses, m1 and m2, they will feel a mutual force of attraction that's proportional to their masses and inversely proportional to the square of their distance. Now, Newton himself actually worried about something that he never solved, and that was this problem of action at a distance. So the question was, how does mass 1 know about mass 2? How do they influence each other? Now, in modern physics language, we would ask that same question as what mediates the interaction. But in Newton's time, and in fact, much before him, Aristotle were also worried about how objects influence each other without actually being in each other's vicinity or having some other way of contact. Now, this problem didn't really get solved till our next hero of gravity came along a few hundred years later, and that was Einstein. And as you all know, Einstein told us gravity is not a force. Gravity is actually the warpage of space-time. Einstein, like Newton, wrote an equation. And unlike Newton's equation, Einstein's equation was really nasty. And it actually was so nasty that it took almost 100 years to come up with reasonable solutions to Einstein's equations. But Einstein's picture of gravity was, it's not a force. You can think of space-time as a grid or a membrane, and when you put a massive object in the middle of that membrane, it will deform it. And then if you put a test particle, like at the edge of it, that test particle must follow the curvature of space-time, and that's what sets up the gravitational interaction. And so that would be what would happen in the static picture of an object sitting in space-time. Now, what if you instead accelerated this object? Instead of it just sitting around, what if it was in an orbit, as might be this pair of neutron stars or black holes? Then, out of Einstein's equations popped these waves, gravitational waves he called them. And what they are essentially, they're actually ripples of the space-time fabric itself. They radiate outwards from the source. They travel at the speed of light in Einstein's theory. And they, you can think of them, if you want to visualize them, you can think of them as what would happen if you dropped a rock on the surface of a pond, and then the ripple would spread out away from the source. Okay, so that was Einstein's gravitational waves. Now, Einstein himself was never very happy about these. So he actually gave us this complete description, complete mathematical framework for gravity between 1915 and 1918. He wrote 3 seminal papers on general relativity that sort of got this going. Now, in 1918, Schwarzschild proposed stars that had, based on Einstein's equations, he proposed stars that had so much mass in such a small volume that even light could not escape their gravitational pull. It turns out Einstein did not like these dark stars. That's what they were called at the time. They were called dark stars. Today we know them as black holes. Then, as Einstein vacillated about gravitational waves, in 1936 he actually submitted a retraction in a paper with Rosen. If you guys know Rosen of EPR, so that Rosen. And then in the same year he retracted the retraction. So, and the paper that he submitted had a title that said, "Do gravitational waves exist?" That was the title. And then if you read shortly into the abstract, you would say that their conclusion was no. And so he actually, so the story that's attached to this paper is actually pretty fun. So I'll tell it to you. So he writes this paper with Rosen. And then they submitted to Physical Review. At the time, there was no Physical Review letters ABC. It was Physical Review. That was the journal for physicists. And it turns out 1936 was the first year that Physical Review instituted the peer review process. Before that, you sent your article in. The editor would look at it and decide if it was good enough or not. So this peer review process sent the paper out. And in fact, it turned out, we later learned, that was Robertson of the Robertson-Walker metric was the reviewer for the paper, and sent back a rebuttal saying this paper is not correct, and here are the reasons why. And so Einstein wrote to the editor of Physical Review, I believe it was a man by the name of Boyd, and wrote a letter saying, I sent you this paper for publication, not for your comments. And then after that, he never, what's that? It is of Robertson Walker, yeah. So after that, he never published in Physical Review again. Okay, so I guess when you're Einstein, you can. By the way, that paper that Robertson found was wrong, and in fact we now know was wrong, was published. So then Rosen sent it off to an obscure journal called the Journal of the Franklin Institute. So it is still published, but it was not published in Physical Review. All right, so that's a story. That was so the point being that Einstein was deeply uncomfortable with gravitational waves. In his 1916 paper, he wrote, if you translate it from the original German, he wrote, "These gravitational waves will never amount to anything useful." And then in 1936, of course, he wrote saying they don't even exist. His worry was that they were some kind of phenomenon that was part of the metric or the coordinates and not really a physical phenomenon. Okay, so. The doubts and controversy about whether they even exist finally subsided in a very, very important meeting that happened in 1957 in Chapel Hill. And in this meeting, this is actually sort of almost the birth of the field of detection of gravitational waves, because there was, until then, right from the late 1910s, until 1957, people had been thinking mostly about sources. They were trying to understand how do you model or solve the Einstein equations to ask what does a source do, how does it emit. Now, in 1957, at this conference, Felix Pirani was the first person we know of who asked a very different question. He said, to hell with the sources, why don't we just look at what gravitational waves do far away from a source? Why don't we ask how do we model their behavior and their measurability? So he was the first person to actually think about what would they do far away from a source, maybe here on the Earth, and he first formulated that they should interact with light. Then the calculations that Scott showed you earlier, and I showed you a little bit of how the light path changes because of the gravitational wave, was initiated by Pirani. Okay? Now, as an experimentalist, I love to remind everybody that experiment and observation always have the final say. Whether Einstein was right, whether he retracted a paper, whether people discuss this at Chapel Hill, in the end you have to ask, what does nature do? So we can ask, what does nature do? So the first part of that story is that neutron stars were actually proposed by Body and Zwicky in 1934. The first neutron stars, or the rotating neutron stars, were proposed in 1967 by Piccini and Gold, and in that same year, the first pulsar was observed by Bell and Hewish. Okay, so the reason why these are important benchmarks is because in Einstein's time, people didn't have evidence that objects like neutron stars and black holes existed. And if you actually plug into the quadrupolar formula that you've seen earlier, the numbers for what would an ordinary binary star system radiate in terms of gravitational waves, they are really, really laughably small. And so Einstein was kind of right to not take the idea of gravitational waves being useful seriously. But then came this man, Joe Weber, and in 1969, he announces to the world that he has detected gravitational waves using this object that's called a bar detector. And the important connection to the 1957 Chapel Hill conference is that Weber was in the room when Pirani did his original calculation of showing what happens if you attach a spring and a mass system together, and what happens to a gravitational wave as it passes through that system. So his detector is this bar. It's instrumented with these very sensitive piezoelectric sensors that measure the vibrations of the bar. So the idea is if a gravitational wave hits the bar will start ringing. And it'll ring like a wine glass if you ping it. And in the case of most bars, these are around kilohertz in a very narrow bandwidth. So he makes this announcement. And these bars were at the time seen as relatively reproducible objects, so it sets the world on fire. A number of very prominent physicists get involved in making their own bars. Okay? And so then there's this proliferation of bar detectors, and no one can reproduce Weber's detections. Now, Weber's detections were very interesting because Weber had two bars. So he had a bar at the University of Maryland, and he had another bar at Fermilab. And he was actually seeing coincident signals between the two bars at presumably had a sidereal day period. So he was very convinced that this was something astrophysical. No one else could reproduce that, but another very important thing happened out of Weber's claims, and that was that until that time, people hadn't really carefully calculated what would you expect the amplitude of the gravitational wave strain to be from these newly discovered objects, okay? And that will come next in my story. Anyway, Weber makes this announcement. It's eventually proven to be wrong. But then in 1971, the first black hole is discovered. So the stage is getting set for very exciting things. And then eventually in 1974, a very important thing happens, which is that Hulse and Taylor discover a binary neutron star system. And the binary neutron star system allows them, because of using pulsar timing, using the radio telescope, they could very carefully measure the orbital period of the binary. And over some number of years, they measured that the orbital period was decaying. And so this is their data starting in 1974 and going on. They have new data since then, but this one ended in 2005. And on the vertical scale is just the decay of the orbital period versus time. The data points are their measurement, and the solid line is not a fit. It is an exact prediction using Einstein's formula for how this system, if you measure the parameters of the system well enough, of the astrophysical system, you plug it into the formula, and it matched this well. Now, this, of course, greatly impressed Sweden, and they got the Nobel Prize for this discovery in 1993. And this was really, in the end, when, I have to say, when we ask what, is any of this correct, this is when we start believing that this might be true, that, that there was this observation of an orbital period decay measured by using light. It was, it was the radio emission of the pulsar that did it, but there we have it. Now, Einstein's ambivalence was justified. I know the first observations of observational evidence for neutron stars and black holes didn't come in his lifetime. He died in 1955. And so a really remarkable thing is that even though he was so ambivalent about it, his theory beautifully and accurately describes gravity, space-time, and black holes. So now we fast forward to 2006. So this is now 90 years after Einstein first gave us the general relativity. And now for the first time, we have both mathematical and computational tools that are sophisticated enough that we can actually model the coalescence of a pair of black holes. I don't know. So here we have it. On the bottom here, you'll see the strain signal accumulating, and the top is just a two-dimensional cut through a four-dimensional space-time. The shape of the surface is the space-time distortion. The color coding tells you about the rate at which clocks are ticking, and then the arrows are telling you about the dragging field. So here are the black holes. They're orbiting each other, losing energy to gravitational waves. And as they do that, they're getting closer and closer. Their funnels are now going to start to combine. And then the movie will slow down and actually stop when the horizons touch. And you'll see that the space-time distortion is at its maximum then. And then there will be a short period of the two black holes merging together and wobbling. And then this system goes quiet, never to be seen or heard again, in any form. This is actually the most remarkable thing. No light, no waves, because once it's a single black hole, it's not got a quadrupolar term anymore, okay? So this guy will live lonely ever after, but has sent out a message to the world, right? Okay, and you can see that this is an incredible, decades-long effort to solve Einstein's equations numerically to get to this point where we can simulate movement. Now, a lot of the things that you heard from Scott works on systems that you can, only if you have a brain as big as his, actually solve analytically. But when you get to sort of equal mass black holes with arbitrary spin, it really you have to go to the numerical phase. Not so much for the in-spiral, but actually for the merger phase. Okay. Now, again, in the late 1960s, Kip Thorne was among the early pioneers to calculate from these newly discovered neutron stars and black hole systems what would be the amplitude of the gravitational wave if you put a pair of neutron stars in a galaxy not too far from our own. And in fact, this was the number that he came up with. This is a strain of 10 to the minus 21, and this would be, the shape of the signal would be this characteristic chirp that you're all used to. Now, how can we think about how to design, if nature would allow us to design our very own gravitational wave source? How might we do it? And to do that, we have two things we want to look at. So this quantity here is the luminosity in gravitational waves, and it's scaled. So there are two constants, of course, the speed of light to the 5th power over gravitational constant. And then there's the Schwarzschild radius over the distance scale of the object itself, so the size of the object. And the Schwarzschild radius is basically the size of an object of mass m, such that it will become a black hole, right? And then to the 6th power is the velocity over c, where velocity again is the speed at which the information crosses this astrophysical object. So you can see right away from here that you need two things. You need the object to be very compact. We need an object that should be approaching its Schwarzschild radius, and you need it to be relativistic. And you win very, very big with the relativistic part because of that 6th power. So that's how we would design such a source. So you'd have lots of compact mass, and you can see neutron stars and black holes are good for that. And you'd need rapid and relativistic accelerations, so orbits, explosions, collisions. And as soon as you do that, then you know right away that colliding compact objects like neutron stars and black holes will be a reasonable source, as would supernovae. And then not so easily encoded in this formula, but something that I'll say personally, the thing that drove me into this field was the prospect of seeing gravitational waves from the early universe. Okay? So why are those so special? Those are so special because when we look back in time at the early universe, the information we have so far from the early universe comes to us from our old window, light. And it turns out that when the universe was hot and young, it was too hot and dense for photons to decouple. So the earliest moment in time when the photons could separate from the matter and start streaming to us was when the universe was about 400,000 years old. Now, gravitational waves, on the other hand, they're very aloof. They actually do not interact with matter very much at all, and as a result, those have been streaming to us from the very earliest moments. So I'll give you the scale. If you could make the sensitivity of advanced LIGO roughly a factor of 100,000 better, 100,000, yes, I said that right, 10 to the 5 better, then you would be sensitive to this primordial background of gravitational waves at a time when the universe was 10 to the minus 22 seconds old. So this was the draw for me. It was like I wanted to see all the way back there. Now personally, I don't believe that these kinds of instruments will be able to do that in my lifetime. So I will die, but I'll leave it to the young people to work on this, because this is the coolest thing that you could do with gravitational waves. Nothing is going to bring you that information of the early universe. Light can't do it, neutrinos are too weak, and so this is the way. If you want to see the beginning, you got to make better instruments, okay? All right, and then of course there's always the promise of things we didn't expect, and we always are hoping for those things. Okay, so now comes the part about detecting gravitational waves. So to detect gravitational waves, we need to know a little bit about what do they do here on the Earth. Are they measurable? So we know they're ripples of space-time. They travel at the speed of light. A very important property is that they compress and stretch the space-time itself. And we've talked a great deal about that. So the change in distance, they change distances between freely floating objects, and the amount by which they change distance is proportional to their amplitude and to the spacing between the freely floating, free-falling objects. So Kip Thorne already has told us that we should expect an amplitude of about 10 to the minus 21. And so you can immediately put a scale on it. If I'm a space-time object of about 1 meter, so if this wave were to pass through me, my height would change by 10 to the minus 21 meters. That's 1,000,000 times smaller than a single proton. So, pretty hard to do, okay? But not for this man. This is Ray Weiss. And Ray Weiss, again in the late 1960s, Ray Weiss was not at the famous 1957 conference. Ray Weiss got into thinking about gravitational waves because he was a professor at MIT, and he was assigned to teach a course on general relativity. And he was actually an atomic physicist. He had never thought about general relativity in space-time. And he will say he was one day ahead of his students. But in trying to understand, he asked the same question: are gravitational waves measurable or detectable? And in that, he came across Pirani's original calculation from the 1957 conference, and he used that to work out how the gravitational waves would interact with an interferometer. And so here is the cartoon of the interferometer, and Scott has shown a version of this too, but what you see, of course, is that as the gravitational wave passes through, the amount of light at the output changes. You either get a lot of light, no light, or everything in between, and having come to my talks, you now know we try to operate where there's virtually no light, and then a little bit of light leaks out, and that's what we measure. Now, there's another historical thing to this that was important. Ray Weiss at the time was working on atomic fountains, and a historical marker to mark this time was that in 1960, the laser was invented. So he was using laser. So he also understood the importance of the coherent light source. The other thing, so other people at this time also had thought about using interferometers for gravitational waves, including someone by the name of Bob Forward, who had actually worked with Joe Weber, and so there were other people who think about it. But the thing that Weiss did was twofold. The first thing he did was he was the first person to understand that it was completely insane and impossible to consider measuring changes in distance of 10 to the minus 21 meters. So he was the person who proposed that we should make these detectors kilometers long. Then you would only have to make a measurement of 10 to the minus 18 meters. And that, he said, was okay. And he said that in about 1970. I told you earlier, I'll tell you again, he wrote this up in an unpublished paper. It was in a report where he worked out all the noise sources that you would have to tackle for a 4-kilometer detector to reach the sensitivity of 10 to the minus 18 meters. Then another remarkable thing happened. So that was in 1972. In 1975, Weiss and Thorne met for the first time. And they met also, this is one of those amazing accidents that allowed, important science to be possible. So they were both in Washington, D.C., Weiss from MIT and Thorne from Caltech. They were both in Washington, D.C. for some kind of review of some scientific project. And there was some kind of screw up with Thorne's hotel room reservation. So Thorne didn't have a hotel room. So Weiss says to Thorne, you can come stay in my room. I have an extra bed. And then the story that he tells is that they were up all night discussing Weiss's idea of how you might make this measurement and Thorne's ideas of what sources would be possible. And in that hotel room overnight, LIGO was born. So that then became the thing we see today. So there's LIGO. And so LIGO, as you know, is these 4-kilometer long detectors, one in Washington State in the desert, one in Louisiana in the pine forest. And you can see this cartoon of the interferometer is now replicated, but on the kilometer scale. Now, in case you've forgotten, I'm going to remind you of something I said in my lectures yesterday, and for anyone who's new in the room. There were two important things to achieve this 10 to the minus 18 meters sensitivity, right? The first is you have to keep these mirrors very, very still. And to do that, the mirrors are, we use these active seismic isolation systems, active because we measure the noise and cancel it. And that got us down to something like 10 to the minus 13 meters per root hertz, or around 100 hertz. And then we also suspend the mirrors of LIGO from a chain of four pendula, and between the combination of this noise cancellation and this filtering, we get down to 10 to the minus 18 meters. So now we have these mirrors that are still at the level of 10 to the minus 18 meters, and we have the task of measuring those small motions. And to measure those small motions, of course, we use light. Now, light is our meter stick here, and what we do is we use lots and lots of photons to average over the noise of each photon, and that's how we make the measurement. And so we have a hefty, powerful laser, and then we have Fabry-Perot cavities in each arm of the interferometer to take this 200-watt laser and bump it up to a circulating power of 750 kilowatts. Okay? So that's the technologies that are used. And then comes our third Nobel laureate, which is I should say, this was funded by the National Science Foundation in the U.S. Pretty much from 1975 onwards, when Thorne and Weiss went to the NSF and said, we have this idea, we want to do it. Initially, it was funded at a low level, and then in 1989, the big instruments were funded. Okay, and right around that time, in the early 1990s, Barry Barish took over as the director of the LIGO observatories and is sort of credited with going from the ideas and laboratory science of Weiss and Thorne to building these national facilities. Okay? So now we fast forward, LIGO is built, we fast forward to, I just want to say, LIGO's not the only game in town, even though it would sound that way from what I say, but there is also a 3-kilometer detector Virgo in Italy, and that's operational along with LIGO, and then under construction and soon to be operational is a 3-kilometer detector in Japan called Kagra. This detector is actually in the Kamioka mine, just in the same location as the Super K neutrino experiment. There's a plan to build a LIGO detector in India. And then you heard from Scott also about the space detector, LISA. Now we fast forward to the 14th day of the 9th month of 2015, and that's when the first binary black hole was detected by LIGO. And here is what was seen. So I told you at the beginning of my talk that my most favorite picture in astronomy was that composite of Cassiopeia. Well, now it's this one. No surprise. I wear it on my shirts. I wear it in my hat. I will admit, though, that I have not covered the picture of my kids with this yet. But here we go. So yes, there are some really remarkable things to see about this picture. Even though you've seen it many, many times, I want to show it to you with a slightly different lens. So there's strain on the vertical axis in units of a part in 10 to the 21. And on the horizontal axis is, of course, a 200 millisecond span of time. So the first thing to see is that each and every one of these bumps and wiggles is a bump and wiggle of space-time itself. So that's the first thing. You close your eyes and think, okay, space-time is really doing that. The second thing that's kind of amazing is that at the time that these two black holes collided, so which is the maximum in the amplitude of the signal, the strain was 10 to the minus 21. This is a huge check mark for Kip Thorne. He told us that in 1968. Okay? Now, when those gravitational waves pass through the interferometer, the mirrors move by a few times 10 to the minus 18 meters. It's a huge check mark for Ray Weiss. He told us how to do it in 1972. Okay? So you can see that these were the visionaries, and they saw something about nature and then worked on it for 40 years to make it happen, along with a team, of course. But they got it started. Okay, now what do you make of this signal? How do we know these were black holes? How do we know anything about this? So now I'm going to do something that will really, if Badri were here, and maybe even if Scott's here, will really make them cringe. But don't worry about it. For our purposes, this is a very good thing. What can this signal tell you? So I'll give you some rough rules of thumb that are only rough rules of thumb, but they're very helpful. You notice that the signal has 4 properties to it. There's a frequency and a rate of change of frequency, f dot. There's an amplitude and there's a rate of change of amplitude. So from the rate of change of frequency, from the evolution of the frequency, we can infer a composite quantity called the chirp mass, which is some combination of the masses of the two black holes. Now, once you can nail down the mass from the frequency evolution, then the amplitude will give you the distance. It's degenerate with the inclination angle to a weaker degree. So if you want to start looking at these signals and just trying to, as rules of thumb, say, okay, what's the masses, what's the distance, you can start to look at that. Just look at the frequency, f dot term, you get the chirp mass out. Look at the amplitude, you get the distance out. In reality, of course, you have to do a full marginalization over 14 parameters. But I can't do that in my head, so that's what I carry with me. And then finally, from the ring down, the frequency and decay time, you can tell what the mass and spin of the final black hole were. And you put all of those things together, and we learned that this system had masses that were 29 and 36 solar masses. Now here's something that when I first saw these numbers pop out, I really, my heart stopped beating maybe. So at the time that these 30 solar mass black holes collided, they were going at roughly half the speed of light. That was their velocity. Just think about that. We can't accelerate, barely accelerate electrons to the speed of light. And here were these 30 solar mass objects whipping at the speed, half the speed of light. We know that they were 1.3 billion light years away, and we also know that they lost 3 times the mass of the sun to gravitational waves in that collision. And Scott explained how incredibly luminous that was in gravitational waves. But amazingly, there's another thing that's so amazing, right? Despite that incredible luminosity, all they did was tickle these mirrors by 10 to the minus 18 meters, right? So it's just kind of crazy how this all works out. But it did work out, so that's good. All right, we've seen more collisions of black holes since those first ones. In fact, there have been now a total of 10 black holes seen. And I'm just showing you this for morphology. I think you can see a few interesting things. Each of these is plotted on the exact same time scale. So you can see that this is the very first one. It's still the loudest one, the highest SNR one. This one here is very interesting. It was seen 2 years later in July 2017. And this is the one that was actually the farthest, but it was also the heaviest, so the signal was large enough that you could still see it, and also has the most evidence, even though it's very weak evidence for black hole spin. This one happens to be the best localized. Well, these are just little things you can do. At the moment, we're basically understanding what are the variations in black holes, right? So that's what's going on. So these have been a total of 10 detections. I'm going to zoom in on one that I think was very important and interesting. And that was, so here is the first one, the one that everybody knows, the one I just showed you, 150914. And in that first observing run of advanced LIGO, we saw 2 others. We saw 151226 and 151012, okay? Now, I'll tell you another interesting and fun story. See this object LVT 151012, that's got a big spread on the sky? This is the localization of these objects on the sky. So LVT stands for LIGO Virgo Trigger. It didn't have enough signal-to-noise ratio to be elevated to a detection. Once it becomes a detection, then it's a GW. Until then, it's just a trigger. Now, in the meantime, since the time that this picture was made, we did a more detailed analysis and new techniques of cleaning the noise and the data, and LVT has now been elevated to GW, okay? So that's the other thing that you can do in the post-analysis. You can do better than in the initial analysis. But notice that in the first observing run, and even for this GW 17014 is January 2017, notice that they make these huge patches of sky. We don't really know where they are. With 2 LIGO detectors, we can't tell very well where they are. And then in August of 2017, we saw this object, and look how well it's localized. What happened? Anybody want to guess? Oh, sorry? We always use triangulation, but now we could actually triangulate. Virgo came on the air. And as soon as Virgo came on the air, that first detection was localized spectacularly. So let me just show you what would happen. So there's 170814. And with LIGO alone, just LIGO Hanford and LIGO Livingston, we could localize to a 1200 square degree patch of sky. And with Virgo detecting, even though Virgo has about half the sensitivity that LIGO had, you could reduce that to a 60 square degree patch of sky. And so that really, I just want to drive home that more detectors really is important. And I can't tell you how important this was, because 3 days after this, something else really spectacular happened, right? This was August 14, 2017. Now let me just wrap up the black holes discussion by telling you what have we learning. So on the one side, we are thinking of tests of general relativity. On the other side, we're thinking of astrophysics. On the test of general relativity, we can confirm that to the degree that these SNR events allow us to, that the waves really do travel at the speed of light. They do not disperse, and from that we can constrain the mass of the graviton to a number. If that rocks your boat, I mean, to me it's just a number, but we can do that, and that's pretty nice. We also understand that post-Newtonian approximation methods work pretty well for these waveforms that we've been generating, which we use as templates to find the signals. And we also have early evidence that the polarization of gravitational waves favors the pure tensor form of general relativity. These are some of the things we can do. On the astrophysics side, we are able to constrain the rates at which these binary black holes are merging to the number I have here, between sort of 10 and 200 per cubic gigaparsec per year. And we're also searching for evidence of alignments of spin in these black holes. And that's actually a very interesting and important search, because one of the questions that we are left with is how do these binaries form? And you can imagine the two scenarios for the binaries forming. The one scenario is where they're formed already as they're born as twins. So the parent stars were in a binary, and when these collapse into black holes, they continue to be in the binary. And in that case, their spins should be aligned, because you can't really reconcile the mass transfer and the angular momentum of the system if their spins are misaligned if they were already in a binary. On the other hand, if they dynamically capture just by one black hole in a rich, dense cluster meets another black hole and dynamically captures, then there's no reason to expect that their spins should be aligned. So by looking at the alignment of the spins, we can start to understand the formation scenarios for these objects. But now we'll move on to neutron stars. So 3 days after that, after the first joint observation with Virgo, we saw our first neutron star collision, and because neutron stars are not black holes, they have neutrons, we expect to see a very spectacular light show following the collision, which you've heard a great deal about over the last couple of days, but I'll show you what happened. So here's a fun story. So here's frequency. This is actually a spectrogram, it's called. It's time on this axis and frequency on this axis. And the first thing we notice is that this is a classic chirp track, but as soon as you see this, even by eye, you can tell this is not a black hole, because this signal lasted a minute. Okay, compared to under a second to about a second for the black holes, because it's so much lighter. 1.7 seconds later, after the LIGO-Virgo trigger, a bright trigger was seen by the Fermi Gamma Ray Telescope. So that was the gamma ray signal. Now, when these signals were observed, we could localize the signals to a patch of sky that was about 30 square degrees, and it was in the southern hemisphere. So an alert was sent out to the astronomy community, and because it was daytime in the southern hemisphere when we got our alert, the astronomy community had something like 11 hours to prepare for the observations. And that night, about 70 telescopes pointed at the sky to look for this object in this 30 square degree patch of sky. I like to call this sort of the astronomer's night to remember. And indeed, it was a night to remember. This is a very busy plot, but I want you to take away some fun things from it. Here was the LIGO signal, as you saw. Here was the gamma ray telescope trigger. And now look at every single band where observations were made, something was seen. Gravitational waves, gamma rays, X-rays, ultraviolet, optical, infrared, radio. Zoom in on this band of things. These are the optical telescopes that looked for the signal that night. This is the galaxy NGC 4993. And in every case, you see these are all different telescopes. That's what their names are, including the Space Telescope, X-ray Telescope Chandra. And if you look in the crosshairs, you'll see an object. Now, this time on the bottom, it tells you the time after the LIGO-Virgo trigger, so 10 hours, 11 hours, 9 hours after 9 days rather after the trigger. And here is an example of why we're so confident. Here was the same telescope, DLT-40, 20 days earlier. And look in the crosshairs, there's nothing. So it's very clear that something lit up in the sky that night. And this is now a much studied object. Now, I think rather than giving you a long litany of all the observations that were done, I'm going to show you just a movie. It's an artist's movie, but it's kind of fun because it's made by NASA. It's very dramatic. And so you see your two neutron stars are orbiting each other and giving off gravitational waves. Oh, I never hooked up the sound. Hold on. We can't do this without sound because it is very dramatic. You'll just have to. There's the jets, and then there's the kilonova right there. That's the emission, the optical emission, and all the debris that's coming out of the collision. Okay, I forgot to hook up the sound, but you'll see it's a NASA movie, so it's very dramatic. So that's really the story. Initially, those neutron stars were giving off no light. They were only emitting gravitational waves. After the collision, and as you saw from Luciano's talk today, in fact, we have some understanding of what happened even within the first second after the collision where the central object collapsed. But that was the observation. Now, I want to just close this part out by telling you about a single observation, one neutron star collision that is already teaching us about the universe in ways that we haven't been able to observe before. So this is a set of spectra. Look, this is in days, different optical wavelengths that the spectra will be made, and it's based on these spectral features that we can tell what the chemistry of the object is and what elements were present at different times. Okay, so this is just a time lapse movie of the different spectra, and you can see different elements show up at different times. Now, this simply is telling us that elements are being fused in this very neutron-rich environment. So here are some amazing things. Luciano told you earlier today, we've long thought, never been able to confirm, that neutron star mergers were the causes of short gamma ray bursts. And now we have one piece of evidence for that. We saw the neutron stars with gravitational waves. Shortly after that, the gamma ray telescopes saw that. And the chemistry of that that's been worked out theoretically seems to add up as well. So we know that neutron star mergers are the cause of short gamma ray bursts. Another long-time mystery has been that we have an overabundance here on the Earth of heavy elements like gold and platinum and the lanthanide series. And we've always worried about that because we know those can't be fused in the sun. The sun can't fuse elements heavier than about iron 56 because it's more energy costly than the sun has. There's some heavier elements are fused in supernovae, but again, the energetics aren't enough for that. So it's been speculated for decades that heavier elements must be fused in the collisions of neutron stars. And from those spectra I showed you earlier, I think we have evidence for that elements like gold and platinum indeed are being formed in neutron star mergers. And in fact, in 1708-17, many tens of Earth masses of gold were fused. Okay, many Earth masses. Okay. Good. And then finally, another piece of science that's been possible to do is that these are an independent way of measuring the Hubble constant, independent of methods using the propagation of light. And this is something that Scott has worked on a great deal as well. But the measurement of the Hubble constant using light, using two different techniques of light, give two slightly different answers. And now using gravitational waves, we're able to weigh in on that. And it turns out, of course, amazingly, that the answer we get for the Hubble constant with gravitational waves is right between the two measurements with light. But the error bars on our measurement is larger. So we have to get more of these before we can narrow in on that. Okay, so I'm going to tell you, I told you we're opening a new window into the universe. A new window into the universe can't just be the first 10 or 11 objects you see. You have to certainly make instruments better to do that. So I'm going to tell you about one trick we've been using, as you've already heard, about in making the instruments better. And that is to make instruments that have subquantum precision. So this I thought you might enjoy after all the things I told you about vacuum fluctuations. This is actually relatively pretty new. It's in the last couple of years. A high energy theorist has made an actual computer simulation of vacuum fluctuations. So the scale of this box is femtometers. And these are just the fluctuating fields. They remove all particles from the box. So this is just the fluctuating field as would be required by QCD. Okay? And so you can see that this is just as I said, we're surrounded by a popcorn of fluctuations of virtual particles being created and annihilated. And these vacuum fluctuations, of course, bother our measurement. So we've been making these specially engineered states of light. So I want to tell you something that I didn't tell you today. I saved it for this evening because I want to now help you walk out of this room just today with a very intuitive feel for what a squeezed state does for a measurement. So here's the thing. Imagine I give you a ruler, and I ask you to take your ruler and measure the length of a piece of paper. Okay? But my ruler is a quantum ruler, and what that means is that the tick marks on the ruler jitter ever so slightly. The spacing between the tick marks and the height of the tick marks, jittering away. So you make a measurement, and you feel very pleased you got an answer. You make the measurement again, you got a different answer. Again, different answer. And this is quantum mechanical, right? And the tick marks on your ruler, of course, are jittering because of those vacuum fluctuations. So these specially engineered squeeze states of light, what they're equivalent of is that taking the tick marks on your ruler and making the fluctuations in their spacing smaller. Now, normally that would really upset Heisenberg, but you don't upset Heisenberg because what you do is you allow the height of your tick marks to be much more fluctuating. But to measure the length of the piece of paper, the height of the tick mark doesn't matter as long as it got some height at all. So you can actually make this measurement because you allowed the height to flicker more, but you made the spacing flicker less. And that's what a squeeze state is, and that's what we've managed to engineer. And as a result of that, advanced LIGO is now making weekly detections of mergers as opposed to previous observing runs, monthly observations. So here we are, we're launching a new era of gravitational wave astrophysics. You've seen the first direct observations of the actual bumps and wiggles of space-time. If that doesn't give you goosebumps, shame on you. We've confirmed Einstein's theory of general relativity. We've seen the mergers, the collisions of neutron stars and black holes observed literally in real time, and few processes in astrophysics can be observed like that in real time, transient phenomena. And really, as someone who's spent my entire career working on building gravitational wave detectors, it's really nice that the damn instrument worked as well, okay? So, and with this attometer precision that was needed. All right, now I'm going to tell you something. So this is the things we celebrate today. This is why we're excited. But really 100 years from now, probably nobody will be looking at that picture as something iconic. Nobody will be thinking about these attometer precision as all that impressive. Really what we've done is we've made a paradigm shift. For the first time, we've been able to turn on a completely new sense. We're able to use gravity instead of light. And in fact, we can combine gravity and light or lose gravity alone. And we expect that there will be really unimagined objects that we'll see. So that is really the thing that we've done, and that's really the opening of the new window, not this moment in time where we've seen 10 black holes and we have attometer precision in the instruments, I predict. But in 100 years, I won't be around to know if I was right, so it's okay. You guys might be, you guys are going to live a long time. So, all right. So let me just wrap up by taking you through a few of the fun things that happened when the discoveries were first announced. So here was an advertisement. You can see the reflection here as a photograph in a New York City subway that says, "Scientists found gravitational waves in outer space. If only it were that easy to find an apartment in New York City with a walk-in closet." Now, personally, I don't happen to agree with that, but here it was. Then another remarkable thing happened. This is my son. This is not my son. This is my son's friend, Oscar. And on Halloween of that year, so in February, we announced the detection, and Halloween of that year, here was Oscar dressed for Halloween. Okay? And including, by then the Nobel hadn't happened, including his medal. Okay? So I just want to say this really, when the Nobel announcement said a discovery that shook the world, it really kind of did. Who would think anybody would care about discovering gravitational waves and the collisions of black holes? But people did. So then, I've had a really exciting life in science as well. So let me show you a little bit about my adventures at LIGO. So here is me, in 2000. So this is a younger, narrower version of me, standing on the top of the Hanford Observatory building, looking at a wildfire that's threatening the town that's to the east. And so this is up in the desert, and in fact it was, the LIGO has a big water tank there, and that was used to fight the fire. And the other remarkable thing was, I showed you earlier this morning the picture, Hanford is a very happening place, right? I showed the picture of the car that had crashed into the beam tube. So that same concrete beam tube also served as a fire barrier and broke the fire from spreading further east into the town that was next door. So that was a big, great adventure. Now, Hanford's not the only place that has adventures. Here is Louisiana. And you notice this little row of rods here in the building. This is the building 4 kilometers away. It's the N Mirror building. And the row of rods was used to mark a spray of bullets. Okay, so that was a spray of bullets. This is the US. People have guns, and they use them. And in fact, this was the cartoon that showed up in the local newspaper. It said it's hunting seasons, time to set the lasers in self-defense mode, okay? So someone took a shot at LIGO. It's also, so that was an adventurous thing. Here is a picture of me working with Matt Evans at the Hanford Observatory, probably in 2002, 2003. And then here's a picture of me many years later working with my own graduate student at MIT. But you notice we're kind of doing the same things, and I wear the same hat, okay? All right, and as I've told you, my career has been kind of built on taking whatever curve we have for LIGO and asking, what's the next one? What are the technologies we need for the next one? That's what I like to do. So that's a little bit of my story. I'll show you some old pictures. Here is Ray Weiss and his group at MIT in 1993, and that's Weiss, and that's me. There's a couple of other people here that will show up in this picture, same picture, notice 2015. There's Ray Weiss now, there's me, and David Shoemaker and Peter Fritschel are also still here. So it's, some people stick around a long time because it took a long time to get this thing working. Okay, this is me in the lab. This is me doing the gravitational wave dance. Have you guys ever seen the gravitational wave dance? What? Have you never done it? Oh, all right, then I have to show you. What happens when a person gets hit with a gravitational wave? Right? It comes right through you, and this is the gravitational wave dance. I thought you'd all stand up and do it. Oh. Okay, well, this is me doing the gravitational wave dance with Neil deGrasse Tyson. I was teaching it to him. Okay. All right, now this is actually a picture that I really like. This was on the morning of the announcement. This is at the press conference announcing the first discovery. And this is actually an intimate moment I was sharing with my then 9-year-old son. He was sitting in the front row, and I was just saying, "I got you, kid." And someone photographed that and sent it to me. And I like showing that picture because I like to remind people that it's possible to have a career in science and have a family, and both can be rewarding. Okay. This is a trip to Stockholm. Here is Ray Weiss meeting the king. Ray Weiss said the king is a little crazy. So, and then here is the group of people that came. And then this last picture is one that I find very important. I'm not in it because someone was clicking, but I want to remind people that even though the field of physics is filled with men, and the Nobel laureates were all men, etc., these are some of the leaders of the gravitational wave detection business. So I won't name them all because it won't mean much to you. But I just want to say that women do lead, and they're very important for this enterprise. So I'm going to end with a philosophical note about what happened to Galileo. Galileo, we believe, was the first person to point a telescope at the sky. Now, I say we believe because oftentimes we see these through a very Western lens, and so Galileo, the Italian, did it, but maybe some Arab did it before that. We don't know. But this is the first time we have documentation of someone pointing a telescope at the sky, and no one remembers what Galileo saw. And in fact, a toy store telescope is kind of better than his now. It was a little 1.5-inch mirror telescope. But what Galileo did for us is not to say, well, I saw craters on the moon because we see them much better now. I saw rings of Saturn, we see them much better. What he did was he said humans can look at the sky not just through their naked eyes, but with an instrument. And then if you build a better instrument, you will see more. And that's what happened. Since then, we've built 100-inch instruments on the Earth. We've built a 100-inch telescope in space. We're building 25 and 30-meter class telescopes. We've built infrared, gamma ray, X-ray, radio. We've built all other wavelengths of light telescopes. And we've seen the cosmos like no one had ever imagined we could, certainly not Galileo. And I think that's where we are with gravitational waves. We only just built Galileo's telescope. It was a bit more expensive, and it took a little longer, but that's it. And the gravitational wave sky is just the same as light. It spans 20 orders of magnitude in wavelength. Every single one of those wavelengths, it brings us different kinds of information about the universe and also needs different kinds of technologies to be seen. So I leave you with this idea that this is a new window into the universe, but we've only just cracked it open, and your generation and the generations that come will really open it wide. So thank you. Questions? Sure.
At the very beginning, you told that after this merge event, it becomes silent.
Mm-hmm.
But is there any possibility that another black hole will come and they will merge again?
Yeah, there is certainly the possibility, but the likelihoods are very, very small. It has to be, in a dense cluster for it to have some cross section with another black hole. So, and we're learning this. Good. Yeah, no, that's certainly true, and that's a fair correction to what I said. Maybe we'll hear from it again. Maybe we have to throw a black hole at it. So.
When are we going to see a supernova emitting?
So we are sensitive to supernovae with this generation of instruments to supernovae in our own galaxy. The rough rate of supernovae in the galaxy is once per 100 years. The last one was in 1987, in the local galaxy area. It's Poisson distributed. It could be tomorrow. It could be 100 years from now, right? So
the current sensitivity is not good for
not enough at all, unfortunately. Yeah. Other questions?
Do we hope for Lisa to see the other universe?
No, Lisa can't either. So just not sensitive enough. Lisa has sensitivity very similar to initial LIGO. So there has been around for a long time a space experiment called Big Bang Observer that is designed specifically just to look for the early universe gravitational waves. But it's a LISA follow-on, and LISA hasn't even happened. So to think about the follow-on is a little premature.
If I can clarify,
yes.
I was involved in that.
Yes, that was Sterl Finney's thing, right?
That's right. The Big Bang Observer was actually more an intellectual exercise to say what would it take to get down to those kind of things. And it's one of those where it's like, wow, if we had infinite money.
Other questions? Does she have a question for me? Oh, don't be shy. Other questions? I'm sorry?
When you came back?
When do I come back? Whenever he asks me to. This is up to Alikram. so good. Well, thank you, everyone.
So, if no other questions, please thank once again the speaker by a long applause.
Thank you, everyone.